Do you know that some math problems can somehow be solved with physics and it's even much easier? Hello everyone, I'm Manshi. In this video, I will take you on a journey to experience the beauty of interdisciplinary thinking, where different fields can inspire one another. We'll break down the barriers between different subjects, why many mathematical problems can be solved with profound insights and incredibly simple solutions drawn from physics. I'm going to show you several exquisite examples in one go. I'm sure you'll find them enlightening. Click like and subscribe, and let's dive into the world of physics and math. In middle school, you may have probably seen this problem. There are two villages, A and B, and a river. You need to build a ferry, P, on the riverbank such that the sum of the distance from the dock to the two villages is minimized. The middle school approach is to reflect one of the villages, say B, across the riverbank to a new point B'. Then you connect P to B'. Due to the properties of reflection, the distance PB is always equal to PB'. So AP plus PB can be transformed into AP plus PB'. Since A and B' are both fixed points, the shortest path between them is a straight line. The point where this line segment AB' intersects the riverbank is the optimal location for the dock, P star. This is the well-known geometric method in textbook, but today I will give you a fascinating proof from a physics perspective. Imagine the riverbank is a smooth rod, and on this rod is a small ring. The ring is attached to two separate ropes with the other ends at points A and B. Now, imagine this setup is on a horizontal table with holes at A and B. The ropes pass through these holes and are attached to weights of equal mass M. Under the tension, the small ring will slide around and eventually settle at a certain position. You might have already guessed. The position is precisely the optimal dock location we found earlier. Why? We can analyze the forces acting on the ring. Since the ropes are taut, we can focus on the angles alpha and beta between the ropes and the riverbank. Notice that the tension on both sides is equal, both being the gravitational force on the weights mg. This tells us that if alpha and beta are not equal, say beta is smaller, then the horizontal components of the forces will not be equal. The ring will be dragged by force and slide to the right. The same logic applies in the opposite direction. Therefore, for the ring to finally come to a stop point, the angles on both sides must be equal. By constructing a congruent triangle on the right side, it's easy to see that the ring satisfying this condition must be at the intersection of the line segment AB' and the riverbank, which is our conclusion before. Now, from an energy perspective, the system at this point will have the minimum possible energy. This means the sum of the two potential energies of the two weights is at its minimum. Taking the tabletop as the zero potential energy level, for weight A, the length of the hanging rope is L1 minus PA, where L1 is the total length of the left rope. We can express its potential energy as mg times PA minus L1. Similarly, the other weight's potential energy is mg times Pb minus L2. Since L1 and L2 are constants, the minimum potential energy of the system corresponds exactly to the point that minimizes Pa plus Pb. This is also the state of the equilibrium where the forces balance. Thus, we have proven that the optimal position P lies on the line segment AB', which is also the equilibrium point. It's worth mentioning that to ensure all the system's energy is in potential, we usually assume the process happens very slowly, with almost no kinetic energy involved. This is usually known as a quasi-static process. The power of this method is that you can have weights of unequal mass. For instance, if the weight at B is k times m, then based on the expression for gravitational potential energy, we know that the final equilibrium state corresponds to the minimum value of Pa plus k times Pb. Using the same physics approach, we can immediately gain a profound insight from the force equilibrium. Since the rod is smooth, the horizontal forces on the ring must balance. The force from the left is mg times cosine alpha, and from the right is kmg times cosine beta. Setting them equal, you immediately find that the optimal solution P satisfies the equation cosine alpha equals k times cosine beta. With this condition, the solution becomes straightforward. Just think how complicated it would be to derive this conclusion using pure geometry methods. From a physics perspective, however, this condition is almost obvious. If we place A and B on opposite sides of the rod and treat the rod as the boundary between the two different media, then PA corresponds to the time it takes for the light to travel in the upper medium. If we set K to be the refractive index, then K times PB corresponds to the time it takes for the light to travel in the lower medium. The principle that light travels in the path of least time means that this optimal position must be where the forces are in equilibrium, satisfying the condition we just derived. Switching from cosine to sine, this becomes an equation says that the ratio between the sines of the angle of the incidence and the angle of the refraction being equal to the ratio of the refractive indices. Congratulations, you've just discovered Snell's law of refraction. We transformed a physical law of light propagation into a mathematical optimization problem, then back into a completely different physical problem of force analysis, and finally derived an optical law. Isn't that amazing? You might naturally wonder, if this weight method can solve for the minimum sum of two line segments, can it also work for three? Absolutely. For any acute triangle ABC on a plane, we can drill holes at these three vertices, hand identical weights from them, and tie the ends of the three ropes together. These three gravitational forces will pull against each other until they reach a stable position. Here, a classical physics principle comes into play. For three equal forces to be in equilibrium, they must be arranged in a specific way. Any two forces must be symmetric with respect to the line of the third force. This is only possible if the angles between them are all 120 degrees. In fact, the point that minimizes the sum of the distance to the three vertices of a triangle has a special name, the Fermat point. This simple physical derivation instantly reveals a profound geometric property of the Fermat point. The lines connecting it to the three vertices are all 120 degrees apart. Isn't that incredible? In fact, there are more interesting examples where the principle of minimum potential energy quickly yields deep geometric properties of an optimal solution. You may know that light rays emitted from one focus of the ellipse will, after reflecting off the inner surface, converge at the other focus. This means that for any point P on the ellipse, the lines connecting it to the two foci are symmetric with respect to the normal vector at that point. This is why the reflection directs the light to the other focus. Proving this geometric prop of an ellipse using analytic geometry is notoriously difficult. However, we can prove it using an imagined physical process. Imagine an elliptical piece of cardboard. A string of the same length of the major axis of the ellipse is attached between the two foci. Now let's imagine a weight is hanging from this string. As we rotate the cardboard, the string will be pulled taut. According to the definition of an ellipse, this weight will always slide along the edge of the elliptical cardboard. Now we can rotate the cardboard so that the weight is exactly at the point P we want to analyze. Here comes the key part. According to the principle of minimum potential energy, the current orientation of the cardboard must let the weight be at the lowest possible position. This means that the weight is at the very bottom of the ellipse. In other words, the tangent line at point P is horizontal, and the normal line is vertical. On the other hand, due to force equilibrium, the equal tensions in the two parts of the string must be balanced in the horizontal direction. Therefore, the two segments of the string must be symmetric left to right, making the same angle with the vertical direction. And that is exactly the conclusion we wanted. For any point on the circumference of the ellipse, the lines to the two foci are symmetric with respect to the normal at the point, satisfying the law of refraction. You might be getting a little bit tired of all these examples using Hanning waves. Are there any physical methods that can magically solve math problems? Yes, there are. Remember the Cauchy-Schwarz inequality? If you have a set of numbers ai and bi, the square of the sum of their products is less than or equal to the product of the sums of their individual squares. It also has an interesting physical proof. Imagine n infinitely long wooden planks with masses mi, stacked on top of each other on a smooth surface. Each plank has an initial velocity vi. Let's define moving to the right as positive and to the left as negative. Now imagine these planks will create friction with each other until they all stop moving relative to one another and move as a whole. We can use the conservation of momentum to find that the final momentum equals to the initial momentum, which is the sum of mivi. In the end, the entire system becomes a single object, so its momentum is the total mass multiplied by the common final velocity. From these, we can deduce the final velocity. And here comes the crucial part. The total kinetic energy of all the planks will inevitably be lost due to friction. Therefore, the final total kinetic energy must be less than or equal to the initial total kinetic energy. The final total kinetic energy is 1/2 times the total mass times the final velocity squared. The initial total kinetic energy is the sum of the individual kinetic energies of each plank. We can cancel the 1/2, cancel one term from the denominator, and rearrange the terms to get this expression. Look familiar? The square of one expression is less than the product of two others. This already has the flavor of the Cauchy-Schwarz inequality. To turn it into the actual Cauchy-Schwarz inequality, we just need the first sum of the right side to look like the sum of the ai square. This means we can just let mi equals to ai square. Then, to make the other expression on the right look like the sum of bi square, we can let vi equals bi over ai. Substitute this in, and indeed, this is the Cauchy-Schwarz inequality we wanted to prove in the first place. This physical scenario even helps you to see the condition for the equality in the Cauchy-Schwarz inequality at a glance. It happens when there is no relative sliding initially, meaning no energy is lost. This means all initial velocities are identical. This implies that all bi over ai are equal, which is precisely the condition for the equality in the Cauchy-Schwarz inequality. How amazing is that? The classical mechanic problem of stacked planks can prove the Cauchy-Schwarz inequality. And of course, there's a small issue here. What if some ai equals 0 in the Cauchy-Schwarz inequality? I will leave this minor problem as an exercise for the reader. The proof is not difficult. At this point, I wonder if you have sensed an underlying connection between these methods. They all seem to revolve around energy. In fact, this is the core of how many physical methods solve mathematical problems. A physical system will always evolve to its state of lowest energy, and this state is always stable. So from the perspective of its dynamics, for instance, through force analysis, it must be in equilibrium. Force is the negative gradient of the energy. Therefore, we can always construct a physical structure in such a way that its energy function equals our desired objective. For example, the sum of the two line segments, the height of the slide, or the kinetic energy of the system. Then, based on the principle that the lowest energy state naturally implies a force equilibrium, or more rigorously, the gradient of the Hamiltonian is 0, we can deduce many non-trivial structures and geometrical properties of this lowest energy state. Having grasped this secret, mathematicians will even proactively borrow the power of nature physics, using natural physical simulations to find optimal mathematical solutions. For example, we all know that liquids have surface tension, which creates a force that tightens the surface. Such a system corresponds to having a surface tension energy, and its minimum is achieved when the total surface area of the shape is minimized. Such a surface with the minimum area for a given boundary is called a minimal surface. When faced with solving complex optimization for minimal surface given the boundary conditions, rather than painfully calculating partial differential equations by hand, mathematicians will often physically construct the boundary with a metal frame and to dip it into soapy water. The surface tension of the soap film is just good, so it can easily simulate the optimal solution with the minimum surface area that satisfies the condition of the boundary. Physicists are thrilled by this. Mathematicians always say physics is just applied math and can't do without your mathematical tools. Finally, you have to use physical methods to get a mathematical solution. Besides minimal surface, mathematicians also set the objective function of an optimization as energy and then use computers to simulate the evolution of the entire system. They periodically introduce thermodynamic fluctuations like vibrations to seek the optimal value for complex combinatorial optimization problems. For instance, the traveling salesman problem, how to find the shortest possible loop that passes through every point exactly once. This problem is known to be NP-complete, and solving it with traditional algorithms is extremely difficult. But if you treat the total length of the loop as energy and consider local adjustments to the route as local perturbations of particles, then by simulating this physical process, you can allow it to spontaneously find the lowest energy state. This will give you an approximate solution with a very short length. Using physical simulations to find optimal mathematical solutions has a specific name, simulated annealing. If you're interested, we will explain it in detail in a future video. To close out the video, let's talk about one more example using a physics method to prove a mathematical proposition. This time, it doesn't use energy, but the melting and the diffusion of ice. This mathematical theorem is called the Fick's theorem. Imagine you have an infinitely large piece of graph paper, and you draw a polygon on it, with the condition that all its vertices are on the grid points. Fick's theorem says you don't need to use complex methods like cutting and rearranging pieces. You just need to count how many grid points are inside the polygon, call it I, and then count how many are on its boundary, call it B. The area of this polygon A is given by an extremely simple formula. A equals I plus B over 2 minus 1. Isn't that amazing? You can calculate the area just by counting some points. How can we prove this using the physical method? This time, let's imagine the graph paper as a giant perfectly level platform. At every grid point, we place an identical, very small, cylindrical block of ice vertically. Each ice block, when melted, produces exactly 1 unit of water. Now we let all the ice blocks start melting simultaneously. The melted water will spread out evenly in all directions, forming shallow circular ripples. Eventually, when all the ice has melted, the water on the platform will level out due to gravity, forming a water layer of completely uniform depth. And here comes the key part, and the reason we went to the trouble of constructing this scenario. For any polygon with vertices on the grid points, the total amount of water inside it must remain constant throughout the entire process. Why? We can consider any edge of the polygon. One side is the interior of the polygon, the other is the exterior. We assert that the total inflow of the water across this boundary is always equal to the total outflow. Why? Because of symmetry. For the water from any grid point, whether it's inside or outside, we can always find another point that is perfectly centrally symmetric to it, with respect to the midpoint of the edge. For these 2 points, due to perfect symmetry, for every amount of the water one pours into the boundary, the other will simultaneously let the same amount of water flow out. And all the grid points on the plane can be paired up with their counterparts due to this symmetry. Therefore, the net flow across this edge is always zero. Since the net flow across each edge is zero, the total net flow for the entire polygon must also be zero at all times. This means the amount of the water inside the polygon remains constant at all times. Hold on a minute. Then we can calculate the amount of water inside at the beginning. It must be equal to the amount of water inside after an infinite time when the whole place is flooded. The final amount of water, because it's uniformly distributed, will be 1 unit of water per unit of area. So the final amount of water is simply the area of the polygon. Then, how much water was there at the beginning? We can calculate it. For the grid points that are perfectly enclosed inside, they each contribute 1 unit of water. At the vertices, it's a bit more complex. The polygon only gets a sector-shaped portion of the water. For example, if the angle is a right angle, it only gets 1/4 of the unit of water. In general, for any interior angle, the amount of water it gets is the interior angle divided by 360 degrees. So, the total initial amount of water is the number of the interior grid points plus the sum of all the interior angles of vertices divided by the 360 degrees. We learned in middle school that the sum of the interior angles of the n-sided polygon is 180 degrees times n minus 2. Here, n is the number of points on the boundary, b. So, the contribution is b minus 2 times 180 divided by 360. You will find this is exactly equal to b over 2 minus 1. And this brings us back to the Peak theorem from the beginning. Wow, a purely geometric theorem can be proven using the physical process of ice melting. In reality, there are no rigid barriers between academic disciplines. Many different fields share the same structures, methods, and philosophical ideas. We must not confine ourselves and build up our own worlds. Thinking math is just math, physics is just physics, social science is just social science, and art is just art. In fact, seeing the shared essence between different appearances is the true spirit of academic research. I'm Man Shi, a PhD graduate from Tsinghua Institute for Interdisciplinary Information Sciences. If you want to learn more about interesting knowledge in math, remember to subscribe me. See you next time.